Hello and welcome back to the Tin Barn. I'm Pragmatic Lee, and yes, you did indeed read the title of this video correctly. In this video, I'm going to attempt to mount a NEMA 17 stepper motor to my rotary table. This is a Vertex 6-inch rotary table. You'll find this same rotary table on eBay, even on Amazon, sold under several different names. I think Vivor is even selling it now or giving it away. But it's a very common rotary table you'll find in hobby machine shops. Basically, it can be used in two dimensions: standing upright like this, with a workpiece out here, maybe even with a tailstock sitting on the lathe, and you would mill a section, rotate it, whatever, mill another section, and so forth. Can also be used in this position where maybe you don't have the chuck on there, but you got just a fixture plate on the table, and you mount your piece on there, and you cut a radius, mill a radius around, like I did in this handle that I use on my mill vise. So why would I want to put a motor on there? Well, you can get kits to go with these rotary tables that allows you to put dividing plates on it and cut gears. Now, I don't know, well, let me say first off, in the years that I've had the little tin barn shop out here, I've never had a need to cut a gear. That's just me. A lot of you cut gears, maybe cut gears on a regular basis, but for me, I've never had the need to. However, it is kind of intriguing. What's not intriguing to me is on a dividing head where you've got it setting up here, and on that dividing head, between each cut, you've got to make like, I don't know, 12 revolutions and 15 holes, or 6 revolutions and 32 holes to get to the next. Lots of opportunity for errors. Again, if you're paying attention to what you're doing, you probably won't cause an error. But I got to wondering, and I stumbled across a video on YouTube the other day where the whole video was about a different project. The guy was cutting internal gears, internal teeth for a gear. And in that video, I just caught a glimpse of his rotary table, and it had a stepper motor mounted over here. Well, I got to researching that a little bit more and realized several folks had done that. But none of the videos I found showed how they actually built the mount for this. So today's video, or my video today, is going to be how I mount this to the rotary table. Now we'll get into more on the next video of how to make the stepper motor work and how to advance it here. Let's look a little bit first at the ratio before I take this handle off and start trying to make this mount. Let's look at this the ratio between this and this turn. Okay, let's get this handle down here on 0, lined up on 0, with this on 0 as well. This is of course adjustable a little bit here. I've already adjusted it so the two are in sync. So let's pull this around. So I've got the two zeros lined up on here and the 0 there. Now let's see how much this moves for one rotation of this. Remember, on the surface grinder, the handle's on it. The X handle, the big handle, one rotation of it move the table on the x-axis 4 inches. On the Z-axis, the handle on it, one rotation moved 200 thousandths. One handle revolution was 4 inches. The other handle, one revolution, was 200 thousandths. So all that had to come in play before we could program the stepper motor. And the ratio between this and this is going to come into play to make this, to automate or make this work as it should. So let's go one revolution here. And I'm not sure if you can see it, tell it by the parallax, but that moved this 4 degrees. On a 360 revolution, that moved it 4 degrees. So let's do a little math here. 360 divided by 4 is 90. So to rotate this, a workpiece in this chuck, a full 360 degrees, we would have to turn this 90 times, 90 revolutions. Now another indication on this dial that it's 4 degrees, notice that's 0. Now that 30 is halfway, but that's 1 degree there, 2 degrees, 3 degrees, and back to 0 is 4 degrees, and now we're setting at 8 up here. So again, one revolution of this equals 4 degrees on that. 360 divided by 4 degrees says this needs to rotate 90 times to do one revolution. Now let's do a little bit more math. This stepper motor takes 200 steps or 200 pulses to do one revolution. So if we multiply that 90 times 200 equals 18,000 positions that we can put this head in. So with 18,000 possible positions of this head, I think we could probably cut gears with it. We would have a mandrel holding our gear blank in the chuck. We might pull up the tailstock over here to hold the other end of it. But then we would, our spindle on the mill would be over here with the gear cutter. We would cut a gear. We would tell the motor to advance to the next position, cut another slot, and so forth until we've gone all the way around. But again, that's phase 2. Phase 1, we're interested in mounting this motor to this. All right, let's start by taking this handle off. It's got a keyway in there. We need to take that keyway out. Let me slide this back on the table so if I drop it, it don't go down in the floor. All right. Now you know off camera I measured that, and this is a 12 millimeter shaft over here. Our motor is 5 millimeter. So we need to go from 12 millimeter to 5 millimeter. Now I don't want to make a direct couple in this. I could take a piece of stock and bore out a 12 millimeter hole in one end and a 5 in the other end, but that would be very rigid, and no matter how much I try, I'm sure there's going to be just a little bit of flex in the motor as far as when this final mount is. So I got to looking, I went to McMaster Car first and looked at their Lovejoy style couplings. When I say Lovejoy style couplings, this is what I'm talking about, where you would have one end with whatever size you needed on that, say 12 millimeter. The other end would be the other diameter you need, 5 millimeter, and then you have the little rubber spider that goes in between. But that just, I don't know, that just looked like kind of overkill for that. Well, to be honest with you, on the McMaster's Car website, I got pretty much confused in trying to find the metric version of each one of these. And these come in different diameters as well. And so I decided, well, let's just go look on Amazon and see what's on there. And I found these. Never seen that before. It's called a helical beam coupler. This has got a spiral cut in it, and that allows a little bit of flex in each or in any direction. And sure enough, they had these. They're fixed. They're one piece, other than the screws, of course. And they had them in 200 and something different sizes, or combinations of sizes. So I looked, and sure enough, 5 millimeter on one end, 12 on the other. So there I was. All right. I probably need to clean some burrs off of this shaft. But there it is. And as you can see, there's a little bit of wobble in there. So if my mount is not exactly perfect, I've got some play in this helical beam coupler is what it's called. So that's how the two shafts will mount together. But let's look at what it's going to take to, I need to clean some burrs off of that. This plate that's on here has got 3 holes in it. Now they're 5 millimeter holes, and I took my digital calipers, zeroed them out, zeroed that, and then I put some 5 millimeter bolts in them and measured between, or measured that distance. Well, measured or zeroed out on one of them, and then measured that, and that gave me the distance between the holes. Now you may recall my little machinist applets program that I featured in a video several months ago. One of the applets in that program was to tell how many holes you got and the distance between the holes, and it will tell you the bolt hole pattern diameter. So let's look at that right quick. Okay, I might have lost some of you right there. Let me back up just a little bit before we look at laying out the bolt hole pattern. With these two hooked together like this, the motor shaft is hooked to the rotary table shaft. However, if I apply power to the motor is going to turn. It's going to try to twist instead of twisting the shaft in there. So we want a plate mounted here that matches that bolt hole pattern with a hole in the middle that this will go over. This would be rigid onto this. Then we'll take another plate like this and put it on this end, or on the motor, with a hole in the middle for that, and a bolt hole pattern to match these four. Now with those in place like that, we'll cut some round stock legs between each one of them, the 4 corners, and match them together, or bolt these together so the plate on this motor is rigid to the plate over here, and this plate is rigid to the rotary table. So when we apply power to the motor is going to set stationary in regards to the rotary table, and the shafts are going to turn. At least that's the theory. So now let's look at laying out this bolt hole pattern right here. Okay, over at the computer now, and again we got the machinist applets program running, and the applet we're going to select here is the bolt circle. Now we know there are 3 holes in that bolt hole pattern. Now we don't know the circle diameter, that's what we want to calculate. But we measured between the holes and that was 1.091. If we calculate, that tells us our circle diameter is 1.260. So let's go to the lathe or to the mill and lay out that bolt hole pattern. Alright, at the mill, I've got a work stop mounted on the mill vise. Remember, we're going to have 2 of these to do. One of them to match the bolt hole pattern on the rotary table, and then one of them to match the hole pattern on the stepper motor. Now I have 2 pieces of this made out, and I've already milled them till they're square. So let's set the first one in up against this work stop. And quickly find the center of it. Alright, there's our center. I have zeroed out the DRO now. And we'll use that same center on the DRO for this workpiece and the second workpiece. We'll also use that same readings when we put this piece back in. All we're going to do now is do the bolt hole pattern. Then we'll do the bolt hole pattern on the other piece. Then we'll gain the 2 of these together, the 2 pieces together, to drill out the center hole and to put our 4 corner holes in for the separator legs. So let's look over on the DRO now. Alright, up here on the DRO screen, we'll select the bolt hole pattern function, and we're going to use XY axis. I've talked about the various options on this before, XZ, YZ, but we're going to deal with the XY on the mill. Where are we starting from? We're starting from center. The diameter we figured was 1.26. The number of holes is 3. Starting angle is going to be 0, ending angle 360 all the way around. So the first hole says move the x-axis to 0.630. I'm going to be drilling a 13/64, which will give a little bit of clearance for the 5mm. Alright, so on the DRO told us to move. Again, the DRO wants us to move the x-axis until that reads 0. Alright. And what that has done is moved off the center to this first hole position. Now if we look back at the DRO, that was number 1. Number 2 says move the x-axis until this reads 0. X-axis and the y-axis till it reads 0. And I'm just concerned with the thousandths digit on there. I'm not concerned with tenths. So now this has come to the other side of center and back. And finally, our third hole says leave the X where it is and move the Y again until it reads 0. We have one over here, one back here, and now our third one. All right, there's our bolt hole pattern. Of course, we can't test it yet until we get this center hole. Now let me show you a little something I'm doing here. On one corner, I just took my red marker and marked that. That is, when I put that back in, I'm going to put it just like that, to the same position. In case I'm off, a thousandth or so between milling this, milling this to the same length as it was width. And what I'll do is put another little mark right there to indicate to me that that's the top. On the stepper motor, I determined that the distance between centers on that, and I did it the same way. I put my pointers of my caliper in there, zeroed it out, then put some 3mm socket head cap screws in each one and measure between them. I determined that to be 1.214, which is approximately 32 millimeter, I'm sure is what it was. But we don't necessarily need a bolt hole pattern for this. Since it's 4 equally spaced, I can just divide that 1.214 by 2 and determine we're 0.607 on the Y, on each side of center on the Y and the X. So we got our little red mark on this one, and I'll put a red mark on the top as well. And just be sure that's up to position. Now if we look back up here on the DRO, we're ready to come out of the bolt hole pattern now. If we hit the down arrow again, it tells us it's over. So we come out of the bolt hole pattern now, and we want to come back to that same 0 that we started with. All right, so we're at 0 on both axes. So we're dead in the center of our piece again. Now I'm going to, trust me, I'm watching the DRO, but on the y-axis I want to come back until it reads 0.607 on this side of 0. All right, that bolt hole pattern should match our motor. Now I'm going to deburr the back side of both of these, bring you right back, and we'll, with the same bit set up right here, we're going to drill the 4 corners. Now for the post in between the two of them, I'm going to be using 5/16 round stock. and I'll be drilling and tapping each end for the 3mm in it as well. But what I've determined, to get this pretty close to the edge on both the X and Y, that I need to go 1.09 from center in each direction. So that's what I've done, and just like I did these 4 holes, I'll drill this one, move up to 1.09 on the other side of 0, 1.09 the other side of 0, 1.09 the other side of 0. Okay, I got the 4 corner holes drilled. I've took the drill chuck out, the drill and drill chuck out, and put in a 7/8 annular cutter. And that 7/8 annular cutter will clear this boss that's on the motor and also the one that's on the rotary table shaft. When you're drilling gain pieces like this with an annular cutter, you'll have to stop in between and take that slug out. All right, it's time to do a little deburring and go back to the workbench and see if these match. All right, let's see if it fits. Here's our piece that we did the 3 bolt hole pattern in. Did an annular cutter for this part of the shaft sticking out here and our 4 corner. Let's see, that was the 5mm. One hole will always match. 2 of them, and the 3rd one. All right, there's our 3 bolt hole pattern matched up. Now let's see if our motor matches up. These were the 3mm. Might get lucky, y'all. Either lucky or we made good measurements. All right, those 4 matched up. So now let's take our coupling. And again, what was the name of those? Helical, let's see, helical beam coupler. I'll put the link to these in the description. Try to remember to, just in case you've got an application, may not by any means be this application, but one where you need to match 2 shafts together. All right, this has got the slot for the keyway on there, and this has also got a set screw. I'm going to try to line that set screw up about halfway. Now the motor shaft, it has got a flat on it, and again there's a set screw there. So I'm not going to go all the way with it, and I'll show you why in just a moment. That coupling also has these come 2 in a package, but it also has a slit in it and screws on the side to tighten that down on the shaft as well. So we'll do that in the final. Now what I need to do is get a reasonably accurate measurement between these two plates. And the reason I put this halfway on each one is so I've got a little bit of adjustment in there. All right, I've got it turned around now, so hopefully you can see what I'm doing. I've got this little wedge here I put under this edge just to try to get this the same. It looks a whole lot straighter looking at it by eye than it does through the camera, and again I think that's maybe a little bit of parallax there. But what I want to do on this end over here, I'm going to take my large adjustable parallel and slide it in at the bottom to where it looks right. I'm going to snug that down and then see how it fits on the top. That is about as good as I think I can measure that. And if I got the top and bottom the same, that same distance should be good for the side to side. So if I measure that, if I can find my calipers, 2.440. That's what my legs in between here should be. Let me make a note of that right quick. All right, so what I'm going to do now is cut 4 pieces of that 5/16 to the same length, 2.440, drill and tap both ends of them for the 3mm. And then I think this will be done. Let me get those pieces cut. All right, I got some 5/16 stock in the lathe now. And I'm going to line up my parting tool with that edge, zero out the DRO, and come in 2.440 and part this off. All right, got a good face on that. I'm going to pull this out. And I might need to get another piece. This one's kind of shattered on the end. But what I'll do is cut 4 of these and then clean this little tit up off the end. And I'll bring you back when we get ready to drill and tap them. All right, I've got the 4 pieces cut. And one end of each one of them has got that nasty little tit on the end from the parting tool. So I'll just simply clean that up right quick without changing the length. Well, I can leave that tool on there because I got lots more of these to do. We'll take our small spotting drill or center drill. And we'll take our tap drill for the 3mm. And we'll take our 3mm tap. Slow way down. And I would never try to power tap this if it was steel, but being reasonably soft aluminum, I think it'll be okay. I hope I don't break the tap. Now we'll take one of our 3mm socket head cap screws and be sure we're tapped deep enough. All right, I'm going to do that 7 more times and And then I'll bring you back when we get ready to do the final assembly. I've got our 4 offset posts or connecting rods uh, cut to length, drilled and tapped on both ends. So now let's do a install of them. All right, the motor is mounted to the rotary table now, and the rotary table is a bit top heavy with that chuck hanging out there. But as we can see, we can rotate it by using these offset pins here or posts instead of a round tube. I can get in there with my fingers if I need to rotate this a little bit. And keep in mind, this locking lever, you can disengage and you can actually turn this by hand. So if I needed to position that at a certain point, let's say I wanted to, for whatever reason, start it at 0, and then lock down. All right, in the next video, we're going to look at applying power to this and attempting to make this step in such an orderly fashion that it would be suitable for cutting gears. Hope you've enjoyed this little video on making this mount. We'll see you on the next video.